let me introduce you to today's speaker, Pragathi Praveena from Carnegie Mellon University. Pragathi is a postdoctoral fellow at Robotics Institute at CMU, where she contributes to NSF AI-CARING Institute. Her research explores the intersection of human-robot interaction and computer-supported cooperative work with a focus on developing novel interaction systems that facilitate human-to-human communication and collaboration. Pragathi earned her Ph.D. in computer science from the University of Wisconsin-Madison, with her work supported by funding from NSF and NASA. Her work was nominated for Best Paper at HRI, and she was also selected to be an HRI and RSS Pioneer. Today, she will be presenting the topic of Robot for Tea, insight from designing the Periscope system for supporting remote collaboration. So I invite Pragathi for today's session.
Thanks for the introduction, Suraj. I want to thank the Talking Robotics organizers for this opportunity to share my research on this platform. As Suraj mentioned, I'm Pragathi, and earlier this year I began my postdoc at the Robotics Institute at CMU. Today in my talk, I'll be focusing on my dissertation research that I did at the University of Wisconsin-Madison, where I was a part of the People and Robots Lab directed by William Mutlu. And as part of my dissertation work, I developed a robotic camera system called Periscope to support remote collaboration between two people on physical tasks. So I started conceptualizing this work on remote collaboration during the pandemic. And as I think many of us have faced, the pandemic has had lasting impacts on the way we work. And almost overnight, as one of the articles on the slide notes, we were plunged into an unplanned experiment in work from home. And in order to be able to work with each other remotely, we all leveraged a number of collaborative tools. Some of these already existed, like Zoom, and they saw an accelerated adoption during the pandemic, and some others were developed specifically in response to these new challenges of remote work. Even Talking Robotics, as I recall, started during this period as a means to facilitate knowledge sharing during those isolating times. So at that time, my research was focused on different aspects of teleoperation interfaces and improving ways in which people can access remote spaces through robot arms. So as we all adjusted to the new reality of remote work, I began to wonder how I could extend my research to tackle one of the core challenges we were all facing. How can we work together more effectively while being physically apart? And what role could a robot, especially a highly articulated arm that I was used to working with, play in facilitating that collaboration? And these questions were central to the development of the Periscope system and the direction of my research moving forward. So as a motivating example, this is a video of two people collaborating in a co-located setting. And watch how they work together on this task that involves physical tasks. So unlike digital tasks, such as editing a shared document, collaborating on physical tasks remotely presents unique challenges. And the challenge in remote collaboration on physical tasks is really that physical tasks require people to look at physical objects from various angles and in varying levels of detail. And you can see that the person here does it very naturally in this co-located setting, but how do we support this type of collaboration on complex physical tasks in a remote setting? In designing the solution, my goal was to provide remote users with the same level of viewpoint flexibility that you see in a co-located setting on the left, by allowing them to remotely view the workspace through a camera mounted on a highly articulated robot arm. So I'll dive into the details of the robotic camera system in the next few slides. To illustrate how Periscope works, this is the remote collaboration scenario that I worked with. We have two collaborators who are in separate spaces. And on the left, we have a person who is manually doing the physical task, that is the worker. And on the right, we have a remote expert who is providing them guidance on this task. The Periscope robotic camera system was designed to facilitate. We have a camera mounted on a robot arm, and this allows the remote expert to observe physical objects in the worker's environment from multiple angles, and thus collaborate effectively with the worker. So the high articulation of this robotic arm allows for specific views, allows the expert to access those specific views remotely. What this looks like in real life is this workspace on the left, where you have the physical task co-located with the robot and the worker. And on the right, you have a remote expert who can use our interface to see the workspace through the robotic camera. Now I'll show an example video that was recorded from the camera on the robot arm that shows the worker's workspace. Personally, for me, the biggest win of this research was that while working remotely, I was able to use Periscope to run a user study to evaluate Periscope for my dissertation. And I used the system while I was home in India for 6 weeks to design and facilitate the study and coordinate with my collaborator in our lab in Madison. And this is the screen recording of my interface, and you can see my collaborator and I discussing the layout of the room, and he now makes adjustments to the furniture in the room. Okay, so now I'm going to go into some more details about the system. I'll briefly go over some of the other technologies and platforms that have been explored for this remote collaboration problem. There are some solutions that allow the worker to show the expert different views, for example, head-mounted cameras. The issue with these solutions is that they often restrict the remote user's ability to be able to independently control the viewpoint in the remote space and see what they want to see. The expert usually has to explicitly ask the worker to show things, and they don't have agency over their point of view. There are some other solutions that allow the remote user to have some control over the point of view, like a PTZ camera or a telepresence robot. But these solutions don't actually have enough degrees of freedom of movement to allow the remote user the flexibility or even the diversity of viewpoints that is needed to effectively provide guidance for complex physical tasks. And finally, all these solutions are sort of a one-size-fits-all, which can work for simple things like a remote conversation or simple physical tasks. But more complex tasks have nuanced subtasks that may have different requirements for the type of views they require. So our solution with a high degree of freedom robotic arm provides the flexibility and the control that the remote user needs to be able to provide guidance effectively from somewhere else. But for this, we need well-designed control mechanisms because it's non-trivial to easily and intuitively move this robot arm to get good views. So I'm not going to go into too much detail about the design of the control mechanisms in this talk, but it's available in our paper on this Periscope system, and the QR code in the corner goes to that paper. It has information about the technical design, but the core insight is that we want people to be able to have control, as much control as they need, and allow for help from the autonomous robot for the things that they don't need control over. So we have a shared camera control mechanism where the responsibility of view control is shared between the worker, the robot, and the expert, depending on task needs. And there are times when the expert needs precise control, and they can do that through mouse inputs. And there are other times they might be happy with some autonomous view that the robot provides based on its understanding of the environment. Here it's tracking the person's hand. And sometimes the worker has access to information or physical spaces that requires them to have control over the view. And workers can control the camera through gestures or direct physical interaction. The paper goes into detail about the shared camera control design and how we combine inputs and resolve conflicts from these three entities. I'm going to summarize here by saying that our use of the high degree of freedom robotic camera with shared camera control mechanisms allows us to enable collaboration on complex physical tasks because of the ability to provide independent, flexible, and task-dependent control of viewpoints. So what I'm going to focus on in this talk is how it plays out in terms of the collaboration, the human-to-human collaboration that the system is enabling. So I'm going to play a 2-ish minute clip to demonstrate how this works in practice. And in the video, what you'll see is a recording of the screen interface as the expert and the worker discuss some steps involved in wiring up a car stereo system. On the left, there is a camera feed from the robot-mounted camera. There is an annotation toolbox to overlay graphics on the camera feed, a control panel for controlling the robot and the camera view, a 3D view that shows a model of the robot and its surroundings, and the video conferencing link for the worker and the expert to communicate remotely. Both of them have a version of this interface they can access, so it's a symmetrical interface.
We're doing purple. We're doing green. That's right.
We're doing green.
Yeah.
Pull on it, make sure it's good.
Good.
Yep. So where's the black white wire that you were talking about previously?
The ones that come out of the speaker.
Oh, coming out of the speaker, yeah.
So if we get the polarity reversed, I'll just reverse them. We should be able to hear that.
Oh yeah, I see now.
Okay.
Yeah.
Green wires are hooked up.
Yeah. So my point is that
So we just want to power it up. We got a couple minutes here.
Oh, we're good. I'm just trying to see if I can make a determination by looking at these other.
Get the black hooked up to the black and white. Up and
Okay,
this
black.
And this crimp came off.
Yeah. This is what happens. That's okay. We're trying to. There you go.
Okay.
So what we see in the video were some different types of interactions enabled by the system. For example, when the worker was crimping the connector, the expert observed it and without being prompted, gave feedback to the worker to pull on it and make sure that there are no loose connections. And in another instance, we see the worker independently working on wiring the system while the expert decides to independently control the camera so they can troubleshoot a polarity issue. And this issue was brought up by the worker several minutes ago, so it was not part of the video that we saw. But the expert thought that this was a good time to revisit that issue. And another instance was we see that the worker is in a hurry to turn on the system towards the end, but the expert continues to troubleshoot. And because of that, the worker actually discovers a loose connection, which he then resolves. So there's a lot of interesting interactions here regarding contextual feedback and conflict and discovery. And given the potential of this system, I was interested in characterizing its potential use scenarios in the real world. So the application that I explored in collaboration with Boeing was workforce training for physical skills. These types of skills are almost never taught remotely. And even though, especially post the pandemic, so many aspects of our education and workforce training are accessible remotely, physical work is something that is rarely taught this way. And even if it is not necessarily effective. So there is potential for, there's design opportunities in this domain. And also the manufacturing domain is promising as an application area for collaborative systems because robot arms like the one in Periscope are already part of many other workflows. So it's increasingly prevalent and accepted, so they can be an enabling technology for new paradigms of work and training. So a key finding from our user study was that Periscope would have potential as part of a blended instructional approach for workforce training. So the first part is an in-person instruction of the basic skills, which is followed by the second part of remote instruction by an expert who can help the student improve those basic skills that they learned in person and troubleshoot any problems along the way. So I'm going to show a video of an remote instruction session from our user study where there's an instructor and a student working on a task.
And you routed a gray wire through there as well, right?
That right here.
You can strip that one too and hook it up to the other one.
Yeah. Came out, was a little loose. This one came loose, so I have to put that back in.
Tighten it, yep. Might as well hit all 8 of those screws. But you got your screwdriver out, check them all for tightness, make sure they're good.
The action that you saw the student doing in the video is crimping, and the student learned to do it 20 minutes before in the in-person instruction that you see on the left. And the student took 45 seconds to do it when he first learned it, but only took 25 seconds by the time the remote instructor joined. This meant that the student could independently work for an extended period of time and only required sporadic interventions by the instructor. This is an indication of some other qualitative differences that we observed between the in-person and remote instruction. During the initial in-person phase, the flow of information is continuous, with the instructor guiding the student in a very structured and routine format. And the instructions are fairly consistent across all students. But in the remote portion that was focused on skill enhancement and troubleshooting, the dynamic is different. Since the students already had a basic understanding, they worked independently for longer periods, and the instructor only had to intervene sporadically. But this also meant that the interactions were much more open-ended, and each session took a different path, even with the same instructor. So in the video we just watched, the feedback from the instructor to tighten all the screws was very specific to this particular student, and it didn't happen with any other students that they instructed. So with the same instructor across the 3 different students he instructed, the sessions looked very different. So the skill enhancement and troubleshooting aspect that I mentioned aligns closely with a type of training that is provided in manufacturing facilities called workplace coaching. Workers typically receive foundational training in a classroom or lab setting and then get ongoing support from workplace coaches on the shop floor. This type of training is just-in-time training, where workers acquire or refresh necessary skills when it's needed, and ideally in the work environment so that the training is directly applicable to the task at hand. And really, this type of support is more likely to be needed as the nature of work evolves. In an increasingly automated world. Routine tasks are the ones that are being automated away, and the tasks that require human intervention tend to be less frequent and require a higher skill level. So part of what we're trying to do is develop new training methods to support workers for these high skill requirements of non-routine tasks. So remote workplace coaching is an exciting potential application for a collaborative system like Periscope. In the last part of my talk, I will discuss some of my methodological approaches and share some reflections on the overall process. I want to begin by briefly outlining the evolution of the project. We developed the majority of the system early in the project with some tweaks and refinements along the way. Then we conducted an exploratory lab study to gather initial insights. And we collaborated with researchers and trainers at Boeing to co-design another study focusing on workforce training. We carried out a feasibility study with remote instructors from a technical college and engineering students. Finally, we submitted a white paper to Boeing presenting the results of a preliminary analysis of this feasibility study data. So our approach to developing Periscope was to make it as robust as possible to ensure that we could evaluate its potential in the complex and dynamic environments where such systems would be used. A lot of comparable systems are built for very simple tasks, and they fail in more complex environments. And so that meant that we had to invest significant engineering effort into creating a safe and professional interface that could be easily accessed and used over the internet. And the web access was very important because it allowed us to recruit remote instructors from technical colleges. And they were real instructors who had a day job and instructed people in a technical college, but now they could operate the robotic camera from their home or office. So our participants actually, they integrated the study into their workday. So they did remote instruction in the morning with us, and then they went to work for in-person instruction as part of their day job. So our system was operational for almost 2 years, and this allowed us to get actionable feedback from a lot more people than we could have otherwise. In terms of the studies, my methodological approach was inspired from a style of evaluation called formative, qualitative, and opportunistic. So a formative evaluation focuses on understanding the interaction design. And that means what the user sees, hears, or acts on while engaging with the system, rather than a summative evaluation, which would focus on assessing specific features or devices within the system. So a formative evaluation is more valuable in our case because the objective was to gain an understanding of the paradigm rather than focusing on specific features of the system. And in that light, it would be more appropriate to think of the system as a high-fidelity technology probe. A technology probe from the HCI literature is a research tool that is used to explore how people interact with new technologies in real-world settings. And we use the Periscope system as a technology probe for providing users with a hands-on experience to envision this future work practice that is significantly different from what they're familiar with. So it's for something that is so novel, it's really hard to get people to envision its utility. So by being able to interact with a high fidelity functional system, they're able to more easily get familiar with it and give us more actionable feedback. So it would not make sense to evaluate the system itself because the system was not intended as a finished product. So the goal was to evaluate how users engage with a broader paradigm, broader paradigm using this highly articulated robot arm, and envision its potential in their future work practices. Another methodological choice in the study design was to do an opportunistic evaluation, and this is in contrast to a controlled evaluation. Opportunistic evaluations allow for open-ended and natural exploration by users, whereas controlled evaluations have a structured and regulated environment where you isolate specific variables and analyze them. So this is in line with thinking about the system as a probe rather than evaluating the system itself. So we try to maintain key elements of a natural collaboration scenario within our studies. And that meant our workspaces were cluttered 3D workspaces as they would be in a potential use scenario. And our tasks were 25 to 45 minutes long. So they could go in many different ways. We provided very limited instruction to participants on what specific steps to take. They had an overall goal, but they could accomplish it in many different ways. And most importantly, we did not actually require participants to use any specific features of the system. So they had the option not to move the robot at all. And we simply asked them to do what they felt would help. And so, of course, there's a little bit of curiosity as to what the robot does, but at some point when they got familiar with it, it really was that moving the robot provided utility, and so they continued to use it in very specific ways. And as we saw in the videos, it was not, people were using the system's features quite extensively, and it was all through a process of discovery. And again, this opportunistic approach, along with the formative approach, allowed us to evaluate the feasibility of this paradigm of remote collaboration rather than benchmarking the effectiveness of this particular instance of the system. The last thing I want to highlight is that we co-designed the feasibility study with the researchers and trainers from Boeing. So we didn't co-design the system itself with them, but we collaborated on how it would be applied in potential real-world use contexts. So in a way, we were aiming for a research application fit, similar to a product market fit. And our goal in working with Boeing was to ensure that the tasks reflected real-world contexts where the system could be used. The design of the task took a couple of months and incorporated multiple rounds of feedback from Boeing trainers to make sure that it was relevant and practical. So I'm going to end this with some potential extensions. Like if Periscope were to be extended, what might that look like? And I'm going to use some very tiny icons to portray that. So one expert might assist two workers. Each worker is co-located with a robotic camera. This is a different team composition than the one that I worked with during the development of the Periscope system. But this was a potential use case that Boeing had mentioned where a single expert could help multiple workers, and that would make a good use case for application of something like this in the real world. So when the worker has a question, the expert can actively use a robotic camera to assist the worker. I'm using this green shade to indicate that the camera is being actively used by the expert. And in this case, the robot for worker 2 might take initiative and monitor the worker on the expert's behalf. They've used a shade of blue to indicate that it's now a proxy for the expert and is kind of monitoring the worker on the expert's behalf. If worker 2 has a question that the expert is required for, then the expert may choose to switch and help worker 2. So in this case, the robot for worker 1 might now take over as proxy and monitor while the expert is responding to worker 2's question. So this is just a hypothetical scenario, but in this paradigm of work, what is the role of the robot? It changed during the interaction from being a passive tool that the expert is remotely controlling to being the expert's deputy. So there's a possibility for a spectrum of intelligence and autonomy and agency to be displayed by the robot. There's also a human factors question. What kind of cognitive demands does this paradigm of work place on the expert? Helping two workers in the same room is very different from helping two workers who might be in completely different spaces doing very different tasks. There could be other modalities the expert could use, for example, a head-mounted display to see the view, maybe even a virtual reconstruction of the space. And here there is a question of what kind of tasks are better done on the screen interface and what kind of tasks might be better done in a 3D environment. The robot may have more than the ability to just to hold a camera. It might also be able to grab or manipulate objects. And the same robot platform is now used for purposes. And so if the robot is grabbing something, but the expert wants to move it to view something else, how would we design the arbitration of inputs in this case? The robot could also have the ability to move around because of a different form factor. And so how does this change the type of context that the robot can support collaborative work for? And also, what kind of metaphors might this form factor be associated with as being part of this team? And what types of contexts can we support if the expert was co-located with a robot that remote workers can access? So this would be a slightly more symmetric situation, but can change the types of collaboration that can be done. We can also leverage data collected from these interactions to build better task models and models of collaboration and build more autonomy and initiative into the robot teammates. And hopefully this can lead to robots facilitating such collaborative work better. Building such novel robotic systems for effective teamwork is also probably going to require new algorithms, representations, methods, and metrics, all of which are interesting avenues for future research. So that brings me to the end of my talk. I'd like to thank some of my incredible collaborators who contributed to the research I shared today. And thank you all for listening. And I'm happy to answer any questions.
So I was curious to know how you introduce the robot in the setup to the participants of the user study, especially the one who is doing the task. And I would like to know if they had a tendency of projecting any personas of the expert or a different character to the robot in itself. So rather than just a human to human communication, did you see any trends of something emerging in between that adds influences emotions or actions of the users?
Right. Yeah, that's a good question. So the robot was introduced as an interface to the local worker. So we said the remote expert will be logging in through the robot in order to be able to communicate with you. So it was introduced to them as an interface and as a tool. I think, so there were 3 different, I guess, levels of autonomy that the robot could display. And I would say that in the mode where it was most autonomous, some people did attribute some type of agency and persona to it, because it's the expert isn't controlling it. The remote user is not controlling it at that point, and the robot's doing its own thing. So it was almost like the 2 people were connecting over how good or how bad the robot was, and so at that point, it kind of it was separated as an entity, as opposed to when the expert was more actively controlling the robot, which I think is in line with many of the other works on telepresence.
That explains it. And just to add to that, how did you handle the latency which might be arising during the interaction?
Right. So the control was designed to accommodate a slight amount of latency. So the mouse clicks, they don't require like exact real time, like no latency. Just I think, it wasn't that there was no latency. It's just that the controls allowed for that latency to be acceptable to the users, because it was sparse commands. So they kind of send it and they wait, and that allows them to not get frustrated with any tiny bit of latency. But we did have one participant who had sufficient latency over Wi-Fi that they were frustrated, but when they did a wired connection, they were able to work just fine with it. So it could be frustrating if it existed significantly.
Thank you.
Hi, Pragathi.
Wow.
He and I were thinking that this is based off an idea that we were talking about before, but we were thinking about like different contexts that this might your system can maybe be used. So we were thinking like right now, a lot of your systems seem to be focused in like manufacturing, like Boeing context. But we were thinking that maybe it can be used for like remote teaching, or like where it's like in different expert novice dynamics and things like that. Like a robot assistant can help be deployed to like different students, and each student can have their robot, and the robot can help them with like chemistry experiments when there's like a remote teacher across the world or something like that. So those were just some fun ideas where we were brainstorming, but we didn't really have a system for it, and now Periscope seems perfect for that. So we were wondering if like you envision different contexts for your system to be applied in.
Yeah, that's a great idea. I think like a lab context is definitely something where this makes sense. Even really if someone is not across the world, it can be it can be interesting to like connect across spaces even within the same university. And I think depending on the level of expertise, so at the core, the shared control works in such a way that the person who has information about the task is likely the one who's going to move the camera. So, or the agent, it can be a human or the robotic agent. So it's like, yeah, possession of information about the task is kind of proportional to camera movement or the agent in charge of camera movement. So I think depending on the context, that would need to be evaluated. Like the specific shared control mechanisms that were implemented within this system were specific to a remote expert and a local novice. But if those roles are reversed, or if the robot knows more or less in that context, then the specific mechanisms would need to be adjusted for that. But yeah, I think as a framework, it would work, and the shared control would need some tweaking.
Great talk, though. Thank you.
Thank you.
It's time to conclude the session. Thanks, Pragathi, again for accepting our invitation for the seminar and presenting your work in detail and also answering the questions. We look forward to feature you again in this seminar in the future with your other research works. Thank you.
Thank you so much. Thank you, everyone, for attending.